and the whiteboard. And I will introduce the topic of today by recalling something that we talked about last time. So if you remember, the last time we talked about the Dirac delta function, Dirac delta function, not really a function, but it behaves like a function. And we use it in mathematical expressions as a function. And it had some interesting properties. Delta t is equal to 0 when t is not equal to 0. And the integral from negative infinity to infinity really, well, I can write it like this. The integral was equal to 1. So the way we kind of thought of this thing was, well, let's just draw a number line without the y. I want something that goes to 0. So what we thought of this as, it's the limit of these functions that have an area under their curve of 1. So there was an area under the curve here of 1. And we took the limit as these things kind of shrunk in, as they shrunk in but maintained an area of 1. They became narrow and narrower and taller until eventually we ended up with this kind of function that's not really a function, that goes, it's basically infinitely tall and infinitely narrow. But this infinitely tall is kind of like a special infinitely tall, because if we kind of were able to smush it out and make it a little wider than infinitely narrow, then it would have a total area under it of 1. So I might write this as an infinity with a little subscript, special kind of. And we went through the work of applying this to certain things, using it to model certain idealized physical systems. And one of the things that we found was that if we take this Dirac delta function, and we kind of integrated it against another function. So we took this function, whatever its normal value is, and we multiplied it by the output of the Dirac delta function, which was 0 whenever t was not equal to t0, and this kind of special infinity when t was equal to t0. And that special infinity multiplied by the value of ft, so that it worked out perfectly that the area under the curve was just whatever the value of f was at t0. That was a really interesting property. It sort of allowed the Dirac delta function to pick out a particular value of this function using the integral. We're going to kind of expand on this idea today and show that it's a much richer idea, and it relates very deeply to the Laplace transform. So if I were to take this right here, I would notice, first of all, that these upper and lower bounds, this was the point that I was going to try to talk about before. I kind of replace these. Let's just say I replace them with alpha and beta. And I say that alpha and beta are chosen so that t0 is somewhere in between them. So the limits of our integration at least include the t0 somehow. then this is still perfectly valid. So what I'm going to do is I'm going to change things up a little bit. Since I'm going to be integrating the t away, I'm going to replace that with a tau. That'll be sort of my dummy variable. And then I'm going to think of this t0 as being variable. So I'm going to replace that with t. And then I'm going to assume that our special value of t here, or tau in this case, I'm going to assume that it's greater than 0. So when I rewrite this integral, the integral of the Dirac delta function from at tau minus t f of tau d tau, I'm going to go from 0 to t. And whenever I do this, what do I end up with? Well, I just end up with f of t. So this is kind of like an operation that I'm applying to f. So I'm doing some operation f. And what it does is it just spits f back out. It's kind of an identity operation. That's a special property of the Dirac delta function. And an interesting thing we'll note is that if we took the Laplace transform of, let's see, the Laplace transform of delta, or let's call the Laplace transform of f, capital F, and the Laplace transform of delta we saw was 1. When we multiply these together, we get the Laplace transform of f times the Laplace transform of delta is just equal to just capital F. So it's just the Laplace transform of f. What am I really trying to say? It's the Laplace transform of this Dirac function, Dirac delta function. I don't know why the screen is making my writing look so bad. So it's the Laplace transform of this Dirac delta function that we saw before, doing this action on f, this kind of identity action on f. So maybe that's really interesting, and we want to expand this idea. We see that there's some kind of relationship with multiplication. Now, what we would really like, what we had before, was the Laplace transform of AF plus BG. So these are some scalar multiples of two functions. We saw because of the linearity, or this is the definition of linearity of the Laplace transform, that we could commute with addition and scalar multiplication. These are something that's scaling the output of the function by some real number. They're constants. What would be really cool is if we had the Laplace transform of the product of functions was the product of the Laplace transform. Nothing in life is ever that easy. In general, this is not true. Sorry. That would be really cool if that were true, but it is not true. And let's look at a very simple example. The Laplace transform of 1. What was this? This was, I remember. the pop quiz. The reason I'm waiting is because I don't have it written down in my notes. I'm losing confidence in my ability to get it correct. I believe it's 1 over S. Yeah. Oh, okay. There we go. Saved by chat. So if we look at the Laplace transform of 1, well, that's equal to the Laplace transform of 1 times 1. And so if this multiplication were true, then we would have the Laplace transform of 1 times the Laplace transform of 1, which is 1 over S squared, which is not the Laplace transform of 1 times 1, but rather the Laplace transform the Laplace transform of t, right? So this multiplication does not work out in general, but this kind of operation that I've written here as arrow, and we'll make more precise in just a second, this does work. And so that's what we're going to talk about today. So first, I'm going to introduce what this actually is. So we're not going to write it as an arrow because it has this nice identity property, and because it has this relationship to multiplication of the Laplace transforms, we're going to write it like this. So it's going to be written as F star G. We're going to call this the convolution of FG, or F involved with G. Okay, so this operation, this way of combining two functions, this is another, well, let's write it down first, and we'll talk about some things that we can notice about it just by looking at the integral. So it's going to be written as the integral from 0 to t of ft minus tau, g of tau, d tau. And one thing that we'll notice about this is that this is an integral transform. So this is an integral transform. And what was the idea of an integral transform? It was the integral, some integral of some kernel function multiplied by a function of one variable. The kernel function was a function of two variables, and we see that here, right? It's a function of t and tau. The variable that the other function is written with respect to gets integrated away. So the integrand is in terms of t and tau. The tau gets integrated away, and we're left with a function in terms of t. So we could write this as f star g, f convolved with g of t. It's a new function that pops out the other side. And what are some properties of this thing? Well, if we take this, integral right here, and we do a change of variables. So we replace t minus tau with a new variable called c, which unfortunately is a pain to, at least for me, kind of looks like, I can never draw this quite right, and it's not helping. The tablet is making everything worse. But it kind of looks like that. Google it and see how it's supposed to look. And it's called Cassis, so it's a pain to write and it's a pain to pronounce. But for some reason, mathematicians like to use this Greek letter. So we make this change of variables, and what do we get for the integral? It will be now f of Cassis, g of what is tau? Tau is now equal to t minus c, like that. What is the upper and lower limits? If I plug zero, or let's see, if I plug 0 in for tau, 0 in for tau, I get t here. And if I plug in t in for tau, I get 0 here. So it's kind of the integrals going backwards. And what is the c? It is negative d tau. So we get a minus sign, d tau. Calc 2 techniques for rewriting an integral. This is just u substitution. And we know that if we flip the direction of integration, then we get the negative of the integral. And so this becomes the integral from 0 to t of g of t minus, and now instead of writing c, I'll write tau, because I'm getting to the punchline. This is just g star f. So this equality goes down here. So what we ultimately get is that f star g is equal to g star f. So like multiplication, convolution is commutative. That's pretty cool. Now if we do f star convolved with, f convolved with g plus h, and what we get is the integral from 0 to t of f of t minus tau times g of tau plus h of tau d tau. And this distributes, so we get 0 to t f of t minus tau g of tau plus f of t minus tau h of tau, which I should write as d tau. And of course, this splits up as two integrals, which you know what those integrals will be, so I'm going to skip the last step. This is f star g plus f star h. So convolution is distributive. Forgot my phone outside, so I'm going to have to make the window smaller so that I can see what time it is. Okay, so we have like multiplication, convolution is commutative. It's distributive. I won't go through this one, but we have that f star g star h is the same as f star g star h. So if we do this kind of multiple integration, it doesn't matter what order we do it in. I think that's occasionally talked about in the multiple integration section in Calc 3. But anyway, like multiplication, convolution is associative, and so we are justified in writing things like f star g star h, and they are well defined. And another maybe obvious property is that f star 0 is the same as 0 star f, which is 0. So if we convolve with 0, well, we've got a 0, and one function is multiplied with 0. So Anyway, just like multiplication, if we multiply by 0, we get 0. And if we convolve with 0, we get 0 as well. So convolution is kind of a generalized multiplication. It's not the actual multiplication, but it has a lot of properties of multiplication. Now, a couple of properties it does not have. F star 1 in general is not equal to F. So multiplicate or convolution by 1 is not just you don't just get the same thing. It's not the identity operation. And F star F may be negative, unlike multiplication by a real number by itself. Squaring a real number always gives you a non-negative. So convolution has this really interesting behavior that it's very closely related to multiplication. It's kind of a pseudo multiplication. It comes very close to having the properties of multiplication without actually being multiplication. So that's an interesting property. Now, well, I should say really quickly that convolutions appear for reasons other than the reasons we're talking about them today, which is their relationship with the Laplace transform. They're very interesting. Various physical systems that we might be interested in modeling. But that's not the purpose of our conversation today. We want to talk about its relationship with the Laplace transform. So how does that work? Let's say that we find f to be the Laplace transform of little f. So that is written as 1 minus s. I'm going to use c to represent the dummy variable here. Kind of looks like an E, but it's got a tail on the end. At least that's how I draw it. And g of s, we're going to use tau as the dummy variable here. That's tau. G of tau, d tau. Okay, so the this is the Laplace transform of little f and the Laplace transform of little g. And now, getting back to the teaser from the original, from the beginning of the lecture, what happens when we multiply these together? So what is f of s and g of s? That's the integral from 0 to infinity, b to the minus s, c, of c, d c, times the integral from 0 to infinity of b to the minus s tau, g of tau, tau. Now let's see. The integrand of this first integral does not depend on the variable of integration of the second. So I can take all of this. None of this right here depends on tau. So we can combine these two integrals together and get the integral from 0 to infinity of the part that just depends on tau. Well, let's write it like this. E to the minus s tau, g of tau, and then all of the integral that doesn't depend on it. This is 0 to infinity. Put this in parentheses. 0 to infinity, e to the minus s to c, f of c, d c, Okay, so this is with respect to tau, this is just some constant, right? Doesn't depend on tau at all. It's some unknown constant. We have to perform the integral, and it's in terms, it'll be in terms of s, but s with respect to tau. Okay. So let's move this e to the minus s tau into the integral, into the inner integral, to get just g of tau on the outside. Now on the inside, integral from 0 to infinity, e to the minus s tau times e to the minus s c, so e to the minus s tau plus c, f of c, c, okay. Now we're going to do a little change of variables. We're going to rewrite c as e minus tau. So given any tau, we can write c in terms of it. And we get d c is equal to since we want this in terms of t, we're going to get dt. So that's the one that we want. Now, when c is 0, you write this when c is 0, that means that t is equal to, thank you, tablet, t is equal to tau. And when c is equal to infinity, this implies that t is also equal to infinity. So this upper limit. So let's see, we have all the pieces except this right here, the t plus tau plus c. So that will be equal to t. Now we can rewrite this. Integral from 0 to infinity, g of tau times the integral from tau to infinity of e to the minus st f of t minus tau dt d tau. So we haven't messed up the relationship with tau. We've just done a change of variables. Okay. Now, if we look at the region of integration, remember this from Calc 3, then for a given, so tau is going to go from 0 to infinity. There we go. And so for a particular tau, we're going to integrate t from tau to infinity. So if we draw this as a picture to help to incorporate our spatial reasoning, take a little bit of the stress off of our logical reasoning. We draw this axis as tau and this axis as t. Then what we see is that we're going to go from, for a particular tau, so we're going to, at a particular tau, we're going to figure out where t is equal to tau. So that'll be this line with slope 1 here. The t is equal to tau, tau is equal to t. And we're going to integrate from that point. We're going to integrate that from that point, on that point from tau to infinity. And then we're going to move up and we're going to integrate to infinity, and so on like that, right? So it's going to be this triangular, this infinite triangular region for the curve here. Now, so long as all of the rules that we said are needed in order to change the order of integration that we talked about in Calc 3, assuming f and g satisfy all of those, then we can change the order of integration so that instead of integrating over horizontal strips, we're going to integrate over vertical strips. So we're going to go in the, instead of going in the tau direction, we're going to go in the t direction, and we're going to get vertical strips like this, right? So what our integral will end up being is the outer integral will be in terms of t, and it will go from 0 to infinity. Sorry, did I say that right? Of course I did. How would I get that wrong? Yeah, from 0 to infinity. Moving the stuff that depends on t outside of the integral for tau. It doesn't matter what tau is, e to the minus st. And then the integral in the tau direction from 0 to t, f of t minus tau, g of tau, this, and then finally d tau. And this part you will recognize as f star g. We've used our transformations of an integral, all of those rules that we had for rewriting integrals. We've used them to get this in the form of something times f star g. That something is e to the minus st, which we recognize. I forgot the dt on the outside. The outer integrals in terms. So it's times e to the minus st, and then we integrate from 0 to infinity. So of course, this is the Laplace transform of f star g, which, as we said, was equal to f g, which was the Laplace transform of f times the Laplace transform of g. And that's the big theorem. So we'll write this up as a theorem. And we'll call it the convolution theorem. I'm going to make this pen a little more narrow. Maybe a little too narrow. Give that a shot. Okay, so let's state this theorem. If that's exactly the same. That looks awful, but let's just hold our nose and get through it. Now that looks, can't stand looking bad. So if we have f of s, which is the Laplace transform of f of t, and we have g of s, the Laplace transform of some g of t, are, let's see, they exist for s greater than a, where a is some non-negative number. And remember, of course, if we're thinking about this in the s-plane, then the real part of s is bigger than a. Then we have that the product of f of s, g of s is equal to the Laplace transform of f involved g. And similarly, well, let's just say this is true for s greater than a. And going in the other direction, if we were to look at the inverse Laplace transform of the product of two things, right? So if we go through this process of solving one of these problems, we get to the end where we're trying to find the inverse Laplace transform of y, and it can be written as the product of two things that we know how to get the inverse Laplace transform of. Right? Then we can write it in terms of those by using convolution. Right. So if we get to the end of one of these problems and we find that this thing can be written as the product of two things, then we can express what the actual thing is, what the actual lowercase y is that we're looking for, the solution, in terms of an integral. And before I kind of go into why that's such an interesting idea, let's do some examples. Are there any questions at this point, by the way? I'm going to take the opportunity to. Despite the fact that we haven't had class for 3 days, I am totally exhausted. I don't know if you've ever experienced the house buying process, but it is very stressful. Okay. Let's say this is an example. Basically, really tired and completely stressed out of my mind. Let's say at the end of one of these problems that we've been trying to solve, we end up with y of s is equal to a over s squared times s squared plus a squared. This is very close to a form that we recognize. Now, I had planned to kind of do a little, like, this is practice. You can do partial fraction composition here, but we're not going to do that. We're going to go straight into using convolution to do this. So how can this be written? This can be written as 1 over s squared times a over s squared plus a squared. We've only got about 20 minutes. Still a little bit to get through. Okay, now the inverse Laplace transform of this thing is just t. The inverse Laplace transform of this thing is sine of a t. So we can actually say, we can go straight to little y of s, which is the inverse Laplace transform, capital Y, sorry, of t. It's just a letter, but we might as well stick to convention. So this will be t involved with sine of at, right? Well, that was easy. We have the answer. We didn't have to do any partial fraction decomposition. Unfortunately, we end up with an answer that is in terms of an integral. Okay, so that's a little bit of a pain. What's even more of a pain is that you are a student in a calculus class, and this is an integral that's easy enough for you to do. And so your professor, your instructor, will expect you to be able to do this integral. So we'll do this by integration by parts. Our u is going to be t minus tau. Remember, we're integrating in terms of tau, not t. dv is myself a little bit more. dv is equal to sine of a tau d now. And so du is dt, and v is 1 over cosine. So this would be negative a over negative a. Yeah, okay. Cosine. I'm looking at my notes and this is not what I'm ending up. Anyway, let's skip it. I'm going to assume the notes are correct. You can try this one as practice. Okay. So, oh, I see what I did. You are? Anyway, you can solve this one using integration by parts, and you get this. Which, if you check against partial fraction decomposition, you'll see that you get this. So that's the point of that example. Okay, now let's do something a little more general. Let's try y double prime 4y equals g of t. Y of 0 is equal to 3. Y prime of 0 is equal to negative. Now we go through the Laplace transform. What we end up with is s squared, capital Y, minus 3s plus 1 plus 4y equal to g, capital G, s. Now, solving for this, we get y of s is equal to, we can split this up into two pieces. 3s minus 1 over s squared plus 4 plus g of s over s squared plus 4. Now, something to note about this is that the way we've written this depends only on the initial conditions. Well, and let's see. Because this denominator only depends on this stuff, right? Only depends on the left-hand side. So this right here, we can think of as characteristics of the physical system, right? That doesn't depend on the initial conditions, it doesn't depend on the forcing function. It's purely in terms of the physical system that we're talking about. Now this part right up here depends only on the initial conditions and nothing else. And this part right here depends only on the forcing function, nothing. So writing it like this, we see that these things that we intuitively think of as different parts of the physical system can be separated out in the mathematical expression of this. Okay, now let's rewrite this thing as 3s over s squared plus 4 minus 1/2 2 over s squared plus 4, right? Writing this in the form a over s squared plus a squared plus 1/2 times 2 over s squared plus 4 g of s. Okay. Now, these first two we know, 3 cosine 2t minus 1/2 sine 2t plus 1/2. And then this part is sine of 2t, and this part is just the Laplace transform of our forcing function. We're doing this in kind of generality. We're assuming that we don't know exactly what the inverse Laplace transform of this thing is. Or we know what the inverse, we know what g of t is, but we don't know. Let's just assume that we don't know exactly. So this can be written as an integral sine of 2 t minus tau g of tau d tau. Now, if g of tau is a particularly nice function, then we can do this integration. For example, integration by parts. However, we could just leave this as an integral. Let's say that g of tau is some kind of black box function. We don't know exactly what it is, but we can kind of sample it at evenly spaced points throughout time, right? So if we have evenly spaced data points where we know what g of tau is, then we can compute this thing. Numerically. So for example, by Simpson's rule, you remember that from Calc 2. And one of the really interesting things, why this is so useful, normally when we get to a situation where we're confronted with an integral, we think of this as a difficult thing, right? It's really a pain to work out integrals. Integration by parts, you do multiple steps, and all these different integration rules. Sometimes U substitution requires you to apply some cleverness. The U substitution that you need to do is not obvious. However, computing things numerically, computing an integral numerically, is incredibly simple. You just plug it into Simpson's rule. You plug your evenly spaced data points into Simpson's rule and have a computer do it. And that is as easy as things get in situations like this. That's a really fascinating thing about one of these fascinating things that pops up in calculus. Something which is very difficult to do symbolically, it's very easy to do numerically. The situation with a derivative, on the other hand, is exactly the opposite. We think of derivatives being easy to do. Numerically, they're much more difficult. Anyway, I think that's an interesting phenomenon that pops up. Okay, so we were thinking about this thing generally, and we saw that if we end up at the end with this, if we use convolution, we use the convolution theorem and Laplace transform to solve these problems, then we can come up with a solution that is pretty easy to deal with numerically. We can take this a little further, and it gives us some insight into how we think about the solutions to these systems of equations. And the ones that we've been talking about, the ones that represent the harmonic oscillator, damped or undamped, forced or unforced, is the second order linear ODE, possibly non-homogeneous, with constant coefficients, and with an initial condition of y equals y0, and y prime equals y prime. Now, if we take the Laplace transform of this, we actually could very easily derive a complete formula for what capital Y is. So we take the Laplace transform and we always get a s squared plus bs plus c, otherwise known as the characteristic polynomial. times y of s minus as plus b, the derivative of the characteristic polynomial, times y0, our initial condition, minus a times y0, y prime 0, our other initial condition, equals the Laplace transform for forcing function. Now, if we rearrange these things, we can rewrite it in just the same form we had before, where the first part we'll call capital phi. This will be as plus b y0 plus a y prime 0 over the characteristic polynomial. And then we'll have psi of s equals capital G of s over the characteristic polynomial. And what we get is that our capital Y of s is just the sum of these. So our solution must be phi of s plus psi of s. Now I'm using the lowercase Greek letters to represent the inverse Laplace transform. I should write that out. Sorry, it should be in terms of t. So capital phi, little psi is inverse Laplace transform. Okay. Now this part right here is totally algebraic. This part can always, it's completely in terms of s. It can always be solved using partial fraction decomposition. Or something similar. The capital psi of s, however, we can rewrite this thing as h of s times capital G of s. So this is the Laplace transform. Should I call this? It's not quite the forcing function, but it's the Laplace transform of the forcing function. So I'll capitalize forcing function. It's this is something that depends totally on the forcing function. And this part is the denominator. It's 1 over the characteristic polynomial. And so this depends totally on the properties of the system, the intrinsic properties of the system, not what we're doing to it, not how it starts out. This is called the transfer function. And the way we think about this is that we have some kind of physical system. Our input is going to be initial conditions, which we saw how to deal with separately, right? That's just solving that part. It's finding the inverse Laplace transform and getting that part using partial fraction decomposition and the forcing function. So these are things that we're kind of feeding into the physical system. And what comes out is the little y of s, the behavior or the solution of the physical system. And we think of these as, they're sometimes called input-output systems. And this is the idea, is that somehow our physical system transforms the stuff that we're putting in into a solution that without the other side. And so understanding the physical system gives us an understanding of the solutions. Now, if we consider the situation, the simplest possible situation where capital psi of S is just equal to H of S, multiply by 1, then we're saying that the forcing function itself is just 1. Or not the forcing function, but its Laplace transform. But what this gives us is G of S is equal, or keep doing that, G of T is the Dirac delta function. Right? This is kind of a simplified input that we can give to the system so that the way that the system behaves is completely contained in this capital H of S. So we can think of this as really trying to find the solution, the system ay double prime by prime plus cy is equal to delta of t. And because we've separated away the initial conditions part, we can think of this as we're just looking at it, the sort of neutral initial conditions and the purest forcing that we can apply to the system that causes it to do anything. And the solution that we get from this, so the response of the system solution that we get from this is called the impulse response. And the way we can think of this, think of a weight on a spring, or one way to think about this that's kind of useful is into 2 or 3 dimensions, but you can think of it as a bell. And you want to understand physical properties of the bell, right? This is a physical system. It has a vibration, kind of oscillatory solutions like Noah. And how do we figure out physical properties of this? We figure them out by taking a hammer and we hit the bell. You know, one quick strike on the bell applies a certain amount of impulse and it applies it basically instantaneously. So it's well modeled by the Dirac delta function. And then the ringing of the bell is the response of the system. So that tells us something about physical properties. So that's how we kind of think about this. Okay. Maybe the bigger takeaway is that convolution is a useful way to solve these equations. But anyway, I think that's an interesting connection with the actual physical stuff that we're trying to use. Okay, I'll stop here. If you have any questions, I'll stick around for that. Otherwise, I'm getting a really strange text message. I'll stop there and I'll start putting out some recorded videos. See you.